Hello students, our next video is on magnetic moments and energy in a magnetic field. So first we will discuss the magnetic moments, the orbital magnetic moments and the spin magnetic moments and its interaction energy in a magnetic field. Right? Now what is the magnetic moment of an atom? The magnetic moment of a current loop, we know that it is mu L is equal to I into A. So L is for the orbital quantity. So mu L, the direction of mu L is along the direction of current. So how can you calculate the magnetic moment of a current loop when an electron is revolving around the nucleus? So the current, we know that it is equal to minus E by T. So 1 by T is F. So it is equal to minus EF. So that is equal to minus E into V by 2 pi R. This is the frequency. Therefore, mu L you can write it as minus EV by 2 pi Rn into A area pi R square Rn square of the nth orbit. So that is equal to, finally we arrive at this equation, mu L is equal to minus E mvrn by 2m. So mvr, you know that it is the orbital angular momentum L. So mu L is equal to minus EL by 2m. So from this equation, since mu L and L are in opposite directions, so orbital magnetic moment, both mu L and L are in opposite directions. Orbital magnetic moment and the angular momentum are in opposite directions from this negative sign. Now, what is the magnitude of mu L? That is equal to minus E by 2m. We know the magnitude of L is root of L into L plus 1 H cross. So that is equal to minus E H cross by 2m, magnitude of L. So we find a new quantity mu L by L. That is equal to a constant term mu B. That is equal to E H cross by 2m. This term is called the Bohr magneton. Its value is 9.27 into 10 raised to minus 24 ampere square. So this is about the orbital magnetic moment. Now, since the spin frequency is twice larger than the orbital frequency, mu s is equal to minus E by m into s. S is the spin angular momentum. So, mu s is twice that of mu. Okay. Therefore, mu is equal to minus E by m into s. So, on substituting such terms, you get in terms of mu b, it is equal to minus 2 mu b s by h cross. Or mu s by mu b is equal to minus 2 into s by h cross. So, this term is taken as gs. This is called the gyromagnetic ratio. gs is equal to 2 here. Similarly, the corresponding relation for orbital magnetic moment, mu L by mu B, that is equal to minus 1 L by H cross. So here we have GL, the value of GL is equal to 1. So the numerical factor relating the magnetic moment in units of Bohr magneton to angular momentum vector in units of H cross is known as gyromagnetic ratio. That is GS and GL. GL is 1 and GS is 2. So this is a numerical factor relating the magnetic moments in units of Bohr magneton to angular momentum vector in units of H cross. That is mu L by mu B and mu L by mu B. Okay. Now combining the magnetic moments, we know that there will be both orbital moment and spin moment will be there. So the total magnetic moment mu J is equal to mu L plus mu S. Substituting mu L and mu S, we get mu J is equal to minus E by 2m L plus minus E by m S. So mu J is equal to minus E by 2m into L plus 2S. So from this equation we find that mu J may not be directed opposite to J. From these two equations, mu L is opposite to L, mu S is opposite to S. Both are in opposite direction since there are negative terms in both equations. But in the case of mu J, the term is L plus 2s is the vector addition. So it may not be directed opposite to the J. The total, what is J? J is equal to L plus S. So that may not be opposite to mu J. Right? Now angular momentum L and S interact magnetically. So if there is no magnetic field, J is conserved in magnitude and direction. But if B is present, J precesses about B and L and S continue precessing about J. So this precession of J around B give rise to anomalous semen effect, which we'll be dealing later. This is the reason why such an effect appears. The precession of J around B give rise to anomalous semen effect because different orientations of J, which is represented by Mj. These are the orientations of J. Okay, the space quantization quantum number Mj involves slightly different energies in the presence of B. So in the presence of a magnetic field, the Mj will have different orientations and slightly different energies. That is how we explain anomalous semen effect. Right? So next is Larmor precession. Now consider an one electron system having orbital angular momentum L placed in a magnetic field B. So mu L experiences a torque, right? So torque is equal to mu L cross B, which we know it earlier. Mu L substitute as minus EL by 2m into cross B. So torque tend to align the dipole in the direction of B. So we know that torque is also equal to dl by dt also. Since L is a constant in motion, its direction must produce a required change. So in order to as L is a constant of motion, its direction must change to produce the required change. Okay, so L precesses about B. This precession is known as Larmor precession and the frequency is called Larmor frequency. Omega L is equal to EB by 2m. So in order to keep L is a constant in magnitude, but torque is equal to dl by dt. So its direction must change to produce the required change. That is why L precesses about B. And that frequency is called Larmor precession frequency or Larmor frequency. Now the energy of the magnetic moment in a magnetic field. So a magnetic moment mu placed in B experiences a torque. Tau is equal to mu cross B, which we can expand as mu B sin theta. So torque tend to rotate the dipole in the direction of the field. So in order to find the energy, you have to calculate the amount of external work done for rotation. So that is delta is equal to integral from 90 degree to theta for an angle theta, 90 to theta, tau d theta is equal to, substitute tau and we integrate, we get the equation delta is equal to minus mu dot b. This is the external work done for rotation. So that will be conserved as a potential energy of the system. Alright. So for theta is equal to 0, delta is equal to minus mu b, which is the position of minimum energy. And when theta is equal to 180 degree, delta is equal to plus mu b, which is the position of maximum energy. So when we apply a magnetic field for a magnetic moment, the energy will be changed by an amount minus mu dot b. So the energy difference between the two positions is 2 mu b. Okay, the energy difference between two positions will be 2 mu b since the minimum position is minus mu b and the maximum position is plus mu b. So the difference between them is 2 mu b. Right? Now we calculate the angle between L and S, the orbital angular momentum and spin angular momentum vectors. We know that J is equal to L plus S. So J square is equal to L plus S dot L plus S. So on expanding, we get L square plus H square plus 2L dot S, or L dot S equal to J square minus L square minus X square by 2. Or cos theta L dot S can be expanded as ls cos theta, right? So cos theta is equal to j square l minus l square minus s square by 2ls, where theta is the angle between L and S, or cos theta is equal to, what is j square? J into j plus 1, L square L into L plus 1, and S square is equal to S into S plus 1, and here L root of L into L plus 1, and S is equal to root of S into S plus 1. So cos theta is equal to this equation. Okay. Now, if phi is the angle the j vector makes with the z axis. So, j vector makes an angle with the z axis phi. Makes an angle phi with the z axis. May be assumed as the direction of the magnetic field, right? So, cos phi is equal to, which is given by jz by j. So, what is jz? It is mj h cross, and j is root of j into j plus 1 h cross. So when h cross cancelled, mj by root of j into j plus 1. So what can be the value of cos phi, or finally phi? Is the angle j vector makes with the z axis. Since cos phi cannot be 0, why it cannot be 0? The maximum value of j is mj. Maximum value of j is mj, which is always less than j into j plus 1, root of j into j plus 1. So, therefore, j can never align along x-axis. J cannot never align x-axis. Okay. So, we have completed all the stuff related to this spectroscopic notations, and next we will be dealing about the spectra of the different elements in the periodic table in different groups, in alkali metals, in many electron atoms. Okay, in the next video.